Okay, in this video I'm going to take you through the Fischer esterification. The Fischer esterification converts a carboxylic acid to an ester. So you can only really do this with an ester. You can't do this with an amine. You can't make amides this way. You can't really make thioesters this way. And what you do is you take the carboxylic acid, you dissolve it in an alcohol, and then you add catalytic acid. Okay, so I've shown an actual example down here where we make ethyl acetate. All right, and about how you name esters. The esters are always going to be the alcohol component, right? We've got this alcohol component where the O is single bonded, that's an ethyl. And then what the carboxylate component would be, this is an acetate, so ethyl acetate. Okay, so I'm going to go through this mechanism, and it's important that you really need to remove water. So think about what we did in acetal formation. Right, you remember making acetals in chapter 19. We drive the water off. Okay, so acidic conditions. No strong bases. All right, so nucleophiles can't just add straight in here. We'd get an O-, that'd be a strong base. Also, any nucleophile that's strong enough to simply add into this carbonyl is just going to take this proton off, right? So first step is to protonate the carbonyl oxygen. Why protonate the carbonyl oxygen? Why not protonate the OH oxygen? Well, if you protonate the carbonyl oxygen, do this in red. If we protonate the carbonyl oxygen, if you protonate the carbonyl oxygen, you delocalize the positive charge. Really, the OH here is pushing electron density into the carbonyl. Remember, if an OH is bonded to a pi system, it's a donor. And so the carbonyl oxygen is by far the more basic of the oxygens. If we protonate the OH, we get an OH2, and that looks like what you want. You're like, oh, it's a leaving group now, and I can do some chemistry with it. And that's true. Unfortunately, now you've got a positive charge on an atom that's got a partial positive charge, right? It's completely localized there. There's no way to, that oxygen's got a full octet. You can't do resonance stabilization. And so, and this is true, I'll say this and then I'll have to erase it. Anytime you protonate a carbonyl derivative, it's always going to go on the carbonyl oxygen. So if a ketone, aldehyde, any of the carboxylic acid derivatives, you protonate the carbonyl oxygen rather than the group over here. Okay, that's really important. So you should if you're wondering about that, play it again. If you're wondering after that, ask me. Always protonate the carbonyl oxygen. Get rid of this. Okay. So now that you've protonated the acid, now you've got a really good electrophile. And so now ethanol can attack. Neutral ethanol, right? You're in sulfuric acid. You can't pull that proton off. There's not a base to pull this proton off, and ethoxide would just react with the sulfuric acid. So neutral ethanol attacks the carbonyl, protonated carbonyl. We get a tetrahedral intermediate. That H is still on there. All right? And now what we need to do is we need to get this H moved to one of the OHs. The way this is going to work, ethanol, or if you want, you can use HSO4-, but ethanol is actually going to do this. These are all equilibria, by the way. So ethanol will take this acidic proton, and then the OH can take the acidic proton. leaving group, that's cool. So why did I do that? Why did I have something take this proton and then give it right back? Why not just do this? Well, it's a good question, right? And it's one of the drawbacks of using Lewis structure and just drawing arrows wherever you want, okay? So if you look at this, all right, it looks like that H is just right there. Why doesn't that O just grab that H? What's the problem? The problem is this: the base, the electrons on the base have to come from directly opposite the OH. So this O, the acidic H, and the base all have to be in a line. Go back to chapter 3, think about the SN2 mechanism. So now there is no way, in 4 atoms, there's no way to put this O here, right? That O can't be there and have these be bonds. So you can't do just a direct, you can't go, this oxygen can't just grab that proton. Something has to take the proton off and move it around. And that's almost always solvent. Right? So this doesn't happen. You can, and I did this in the acetal mechanism. You've seen this in the acetal mechanism when we've talked about it. You can just go straight over to there by just invoking what we call a solvent-assisted proton transfer. Right? Solvent basically just shuttles. It would actually look a lot more like this when this ethanol would just sit here, would grab the H that's on this oxygen, and then immediately give the other H to the other oxygen. And there you go. You've moved the hydrogen. You haven't violated atomic geometry. Okay, so we're almost done. Now, again, you've got a protonated water. This oxygen can kick that OH out. H2O, that's a positive charge. Make sure you put your charges on all charged atoms. And then water can take this proton. And there you go. You've made ethyl acetate and H3O+. So this is like the acetal, this is very much like the acetal formation reaction. You need to drive the equilibrium. The way we normally drive, in the acetal formation, the equilibrium so favors the ketone or aldehyde that you really need to remove water. Here you don't actually have to do that. You can. Removing the water is fine. But actually, if you use the alcohol as the solvent, right, there's just a ton of ethanol. There's not much water. That shifts the equilibrium toward the ester. In the next video, I'm going to show you how you do acidic hydrolysis, which is just the reverse of this. All right, so the reverse of this process is acidic hydrolysis.